Hello, and welcome back to the course on Physics for Engineers. So we are still on the 10th chapter of this course, which is all about thermodynamics. So before we proceed with the first lesson, let us first review some concepts. So in the previous chapters, we have discussed about, in passing, about densities, different types of densities. You have discussed about the linear mass density, mass per unit length. I don't know if you have discussed about surface mass density, mass per unit area, but definitely in fluids, you have discussed about the volume mass density, which is mass per unit volume. So in this lesson, we will be talking about thermal expansions. These are changes in the size and shape of a material or an object due to application or removal of heat. So thermal expansion is basically, it's either a change in length if you have a linear expansion, or a change in volume of an object due to changes in temperature. So if the temperature is increased, the normal reaction of a material is expansion. So it becomes less dense. It has the same mass, but its volume now increases. That's why its density decreases. So it becomes less dense. So if you decrease the temperature of material, the normal reaction of that material is to contract. So there's contraction. So when an object contracts, it has the same mass, but its volume is smaller, so it has a larger density. So it becomes more dense. So if you have solids are actually more dense as compared to liquids and gases. So if you heat a material, for instance, you're actually expanding the material. So the same thing happens for materials. So if you have a material with a hole in it, the hole will actually expand together with the material. Okay. So if you apply heat to a material and its temperature change, but only its length changes, then that is called linear expansion. So at an initial temperature, its initial length is L sub 0 or L naught, and its initial temperature is T naught. And upon applying heat, its temperature changes to T, and it has a new length now, which is L. And the change in length now, which is the final length minus the initial length, is just given by this equation, where alpha is what we call the coefficient of linear expansion. And the change in temperature, for the changes in temperature, it is recommended to use kelvins or degrees Celsius. So both the Kelvin and the Celsius temperature scales have the same value for the change in temperature. Now, if you apply heat to a material and the whole volume changes, then it's called volume thermal expansion. So if you have initial temperature, initial volume, and you apply heat, and then its temperature changes and its volume expands, then that is volume expansion. So beta here is just the coefficient of volume expansion. So V naught is the initial volume, delta T is the change in temperature, which is either in degrees Celsius or in Kelvin. So these are some coefficients of linear expansion of some materials. So for aluminum, in this list, aluminum has the highest coefficient of linear expansion. And take note, the coefficient of linear expansion, alpha and beta for volume expansion, are all proportional to the change in length and change in volume. Meaning the higher the values of alpha and betas, the higher or the larger the change in length for a given temperature. So this means that aluminum expands faster than brass and copper. So for every material, it also has a separate coefficient of volume expansion. So for aluminum, its coefficient of linear expansion is 2.4 times 10 to the negative 5 Kelvin inverse or Celsius degree inverse. It's just the same. The unit is just the same. And its coefficient of volume expansion is 7.2 times 10 to the negative 5. So from this, you will notice a pattern that the coefficient of volume expansion is just 3 times the coefficient of linear expansion. So for brass, it's 2.0 times 10 to the negative 5. For alpha, and its beta is times 3, so you have 6.0 times 10 to the negative 5 Kelvin inverse, or per Kelvin, or per Celsius degree. Now, let's try to focus on the thermal expansion of water. Okay, if you have water and its temperature is above 4 degrees Celsius and you remove heat from water, then water will contract. And if you increase the temperature of water above 40 degrees Celsius, the water will expand. And similarly, if you have ice and you increase the temperature of ice towards 0 degrees Celsius, the ice will expand. And in contrast, if you have ice and you further remove heat from it, it will contract. Now, that's the normal reaction of a material. If you increase its temperature, it will expand. If you decrease its temperature, it will contract. But water has an anomalous behavior between 0 degrees Celsius and 4 degrees Celsius. So if you increase the temperature from 0 to 4 degrees Celsius, instead of expanding, it will actually contract. It will become more dense. And instead of, if you decrease the temperature of water from 4 degrees Celsius to 0 degrees Celsius, instead of contracting, it will actually expand. So it will become less dense. So ice is actually less dense than water, which means since ice is less dense than water, then ice will float on water. So this is the reason why ice floats on water, because ice is less dense as compared to water. And this is the reason why glass bottle breaks when water inside them freezes. So don't freeze water in a closed glass container, because if you freeze that water will actually expand when it becomes ice and your glass will break. So that one. This is also the reason for leaving things in water to survive. So since ice floats on water, therefore, if you have a lake or any bodies of water, the first level to freeze is the top of the surface of the water. That's the first thing that will freeze. And since it's already frozen, that layer of ice on the surface of the water acts as a protection of the acts as a shield from the environment. So therefore, the bottom part, or the water below the surface, will no longer freeze, and living things such as fish will survive in that environment. So they will no longer freeze. So that one. So thanks to this anomalous behavior of water, living things in water can survive, even in very cold conditions. Okay, so let's now have an example. So this is an example on bridge expansion joints. So I'm sure you have already passed a bridge, of course, and you may have noticed some joints in the bridge which have teeth-like structures. So the purpose of this expansion joints is from the word expansion. So it's for expansion and contraction actually. So there's some gap within the teeth so that when on a very hot day, since the steel will expand, so they will have room for expansion. Because if you don't place things like this in your bridge, your bridge will actually break or buckle. So the steel bed of a suspension bridge, so suspension bridges have steel beds. So the steel bed of a suspension bridge is 200 meters long at 20 degrees Celsius. How much will it expand during a hot day of 40 degrees Celsius? And how much will it contract on a cold day of negative 30 degrees Celsius? Okay. So we are given the initial length, we are given the initial temperature, we are given the the final temperature. So we can now solve for the change in length. So the change in length, so for the first problem, change in length is just alpha, initial length, change in temperature. So alpha for steel, its coefficient of linear expansion is 1.2 times 10 to the negative 5 Kelvin inverse. And then initial length is 200 meters. The change in temperature is the initial or the final is 40 degrees Celsius. The initial is 20 degrees Celsius. So the final unit of that is meters. So the change in length on a or how much will it expand on a hot day of 40 degrees Celsius is 0.048 meters, or in terms of centimeters, that is 4.8 centimeters. So this is actually a very appreciable expansion, 4.8 centimeters. And take note, 40 degrees Celsius temperature is actually not that hot, especially in tropical countries like the Philippines. Now, on a cold day, use the same formula, but now, so you have 1.2, the alpha is the same, the initial length is the same. So on a cold day, the final temperature is negative 30 degrees Celsius minus the initial temperature is 20. The final unit is meters. And you will get a value of negative 0.12 meters, or that's negative 12 centimeters. The negative change in length implies that it is contracting. It's getting smaller. The positive change in length implies that it's getting longer. It's expanding. So on a cold day, since the temperature is decreased, so you will have a negative change in length. Okay. So another example. So this is a material called quartz. So you have a quartz sphere, 8.750 centimeter in diameter at 30 degrees Celsius. If it is heated and its diameter expands to 8.751 centimeter, what is the heated temperature of the sphere? So we are trying to find the final temperature here. We are given the final volume. So basically from that, we can get the change in volume. So the change in volume is just the final volume minus the initial volume. Now, this is a sphere. The volume of a sphere is 4/3 pi r cubed. So we are given its diameter. So the radius is just the diameter over 2. So therefore, in terms of the diameter, the volume is pi d cubed over 6. That one. So the final volume here is pi d cubed over 6, and d here is the final diameter, which is 8.751 centimeters, minus the initial volume, which is pi initial diameter cubed over 6. So this is our change in volume. And this should be equal to beta initial diameter V naught change in temperature. So the change in volume, which is this one, it should be equal to that one. Okay. So we need to find the final temperature. So we just factor some terms here. So you have pi over 6. You have d cubed minus d sub 0 cubed. This is the initial diameter. And it's equal to beta. The initial volume is just pi d naught cubed over 6. So you can actually cancel, multiply both sides or divide both sides by pi over 6. And then change in temperature is just final temperature, which is the unknown, minus the initial temperature, which is known. It's actually 30 degrees Celsius. I'm just going to erase this one. So it's 30 degrees Celsius. So solving for T, we get T is equal to the initial temperature plus D cubed over beta D naught cubed minus 1 over beta. So use the beta value for quartz. You are already given the final diameter and the initial diameter and the initial temperature. This will give you a value of 315.7 degrees Celsius. So this is your final answer. Okay. So the final answer is 315.7 degrees Celsius. Okay, next example. This example is overflow of mercury. So a 200 centimeter cube glass flask is filled to the brim, so up to the top, with mercury at 20 degrees Celsius. How much mercury overflows when the temperature of the system is raised to 100 degrees Celsius? So alpha of the glass is 0.40 times 10 to the negative 5 Celsius degree inverse. Beta for mercury is 18 times 10 to the negative 5 Celsius degree inverse. Okay. So how much mercury overflows? So you need to solve for the change in volume of mercury. And you also need to solve for the change in volume of the glass because you are heating them at the same time. You raise the temperature to 100 degrees Celsius. So there will be a change in volume for the glass and a change in volume for mercury. And the difference of those change in volume is the volume of the overflow. So the overflow volume is just the change in volume of mercury, Hg, minus the change in volume of the glass. So that's the overflow volume. So this is just beta of mercury, initial volume of mercury, change in temperature of mercury, minus beta of the glass, initial volume of the glass. So in this case, the initial volume of mercury and the glass are actually the same. It's 200 centimeter cube. And then change in temperature of the glass. So simplifying, we have beta of mercury minus beta of the glass. They have the same volume. They have the same change in temperature, actually from 20 to 100 degrees Celsius. So converting the initial volume to meter cube, and the change in temperature is 100 minus 20, so you have 80 Celsius degree. So you are given the beta of mercury, but you are not given the beta of glass, but you are given the alpha. But we know that the beta of glass is just 3 times the alpha. So basically, the beta of glass, you can just say 3 alpha of glass. That's the beta of glass, 3 times alpha of glass. You substitute all of the values, and the volume of the overflow will be 2.7 centimeter cube. So actually, in this problem, it's not necessary that you convert your volume to meter cube. You will have a very small answer. So I think you don't need to, unless it's specified in the problem that you use meter cube, standard units. But since it doesn't specify in the problem, so you don't need to convert to meter cube. So centimeter cube is fine. So 2.7 centimeter cube, where centimeter cube or cc is 1 ml. So basically 2.7 ml or 2.7 milliliters of mercury will overflow. Okay. So that's the end of this lesson. So for the next lesson, we will try to investigate what happens when you heat an object, what happens to its temperature and its phase in the topic called calorimetry. So I will see you again in the next lesson.